Suppose you have two probability distributions and you want to know how far apart they are. Not the distance between 2 points, but the gap between two entire shapes of belief. Two competing descriptions of the same uncertain world. KL Divergence answers exactly that, and it quietly powers variational inference, model distillation, and the way we keep fine-tuned language models in check. Today we're unpacking what it actually measures, why it isn't a real distance despite the name, and where it keeps showing up across modern machine learning. Let's build the intuition by following one idea through the picture, because the whole thing rests on a single question about surprise. Start with the true distribution, the one your data actually comes from. Call it P. This is reality, the honest source of the samples you keep observing, and everything else in the story gets measured against it as the reference point. Now bring in an approximation, Q. This is your model's guess at that reality, a simpler or more convenient stand-in that you hope captures the important structure of P. It is almost never exactly right, and whenever we describe data with Q instead of P, we quietly pay a small price for that mismatch. That price is extra surprise. KL Divergence measures the additional bits you incur when you encode data from P using the wrong distribution Q. When the two match perfectly, the divergence is zero, and it grows as they drift apart. It is the information lost when Q stands in for P. Here comes the twist that trips people up. Divergence from P to Q generally does not equal the divergence from Q to P. Direction matters, which is why we call it a divergence rather than a true distance. That asymmetry is genuinely useful, not a bug. So why does everyone hesitate to call this a distance? Look at these two framings side by side. A symmetric distance treats both directions the same. Going from A to B costs exactly what going from B to A costs, and it respects the triangle inequality, so no shortcut ever beats the direct route. That is the comfortable, geometric intuition we all carry around from everyday life, from maps and rulers. KL Divergence breaks that comfort on purpose. It reads the extra surprise from approximating one distribution with another, and swapping the two gives a different number. Minimizing it one way encourages mode-covering behavior. The other way encourages mode-seeking. The direction you pick is a modeling decision with real consequences. Now let's pin down the 3 ideas worth carrying with you, because these are what make KL Divergence show up everywhere. First, it measures how much one probability distribution differs from another. 0 means identical, and larger values mean they diverge more. That single number captures a rich... Alright, let's lock into 4 things worth remembering. KL Divergence measures the extra surprise from using an approximation Q to describe data that truly comes from P. 0 means the two distributions are identical, and the value grows as they pull apart, capturing the information you lose whenever the approximation stands in for the real thing. Because it is asymmetric, it is a divergence and not a true distance, and each direction encourages a different modeling behavior. From variational inference to distillation to RLHF penalties, this one quantity does quiet heavy lifting. When ideas like this finally click for you, Standarity.com has plenty more explainers waiting. See you there.